Thank you for the introduction. Good morning, everyone. I'm Xiaoxiao. I'm a GPU hardware architect from AMD. Today, I will introduce a collaboration work with Duke CEI Lab, the Ecco improving memory bandwidth and capacity for large language model via entropy-aware cache compression. Let me start with a quick summary of what this talk will cover. I will introduce the Ecco, our entropy-based compression algorithm tailored for efficient large language model inference, especially the decoder phase. And I will also work through how we designed hardware block for the decompressor and the compressor to enable the runtime decompression on wait activation, the KV cache data, and also the compression applied on activation and KV cache for at runtime inference. And then last, I will show how Ecco is perform compared to the popular quantization schemes in both accuracy and performance. So I will introduce our motivation shortly. So as the size of the AI model has been increasing rapidly, running large size of the model requires intensive data movement for the weight and also intermediate data. And meanwhile, the machine learning hardware accelerators such as GPU has continued to evolve, improving in both computer capability and also memory throughput. But however, due to the cost and also the hardware limitation, the speed of a memory bandwidth scaling has left behind the compute performance and also the rapid growth in model size. So as a result, most of the large language model running became memory-bound workload, especially in the decoder phase. And their inference performance typically linearly scaled with the size of the model parameter and also the intermediate data due to its the low arithmetic intensity. And applying a compression on such a data helps this workload close the gap between the compute and the memory, and it can also shift the large language inference workload closer to the compute bound region. And in this work, so our goal is to design a compression method that retain the most useful information using fewer bits. And ASIC quantization is is a fundamental technique in model compression. So to evaluate the effectiveness of different quantization scheme, we introduce information entropy and to evaluate the level of the information preserved in the context data and also the real bit overhead to reflect the cost of each of this scheme. As shown in this is the picture on the bottom. That so we compare the three most common and popular quantization scheme: the tensor-wise, channel-wise, and group-wise, with our entropy-based compression. So you can see that our proposed entropy-based compression preserves the most information while using a similar bit overhead as the tensor-wise quantization. So in addition to the effectiveness of the compression algorithm itself, in this work, we also designed a dedicated hardware block for compression and decompression, integrated along with the L2 cache. So with this dedicated hardware block, so it offload the computation overhead from SIMD side. And also in this design, we choose the compressed data block size perfectly aligned with the memory hierarchy. So as in modern GPU architecture, the 32 bytes is used as the sector size for memory transaction. And also most of the cache line are using either 64 byte or 128 byte. So in this work, we choose 64 byte as the comprised block size to strike the balance between minimizing the hardware overhead and also maximizing the bandwidth utilization. And we also use the power 2 as compression ratio on all three types of the data. So to simply the power 2 compression ratio can simplify the alignment in the memory space. Yeah, so for weight and the KV cache data, we use a 4x compression ratio. And so in every group size 128, each data will have average 4 bit. And for the activation, we designed a 2x compression ratio. So this picture shows the details of our entropy-based compression algorithm. So I will explain in detail in steps. So we first group weight and activation into a chunk of 128 elements, and then normalize each group using its own scale to ease the quantization. And the next, the k-mean clustering is applied within each group to replace the value with the central indices. And then we perform another k-mean across groups to enable a shared codebook, reducing the metadata size and also increasing the data reuse. And then next, the quantized value are assigned using round to nearest algorithm, and it can generate compact integer representation. And at the end, we apply a Huffman encoding to compress the frequent value into fewer bits, and then at the end, we pad and clip data to fix 512 bits blocks. So to implement this compression algorithm in hardware efficiently, we address several challenges. So the first one is the Huffman coding has a variable code length. But we observe that the most of the codes falls into 2 to 8 bit range. So to simplify the hardware logic, we restrict all the code are within the range of 2 to 8 bits. And the second challenge is selecting the right k-mean pattern for the KV cache data at runtime is very, very costly using the minimal error matching. And we observe that the most patterns are highly skewed with noticeable difference between the minimum and maximum values. So in this work, we simply compare each group's minimum and maximum to those of candidates' pattern for fast selection. And the third challenge is determining how many k-mean patterns and codebook are truly needed in this work. So we solved this problem by doing a design space exploration, and then we found a sweet point, which is 64 shared k-mean pattern and per tensor, and 4 Huffman codebook per pattern. So with this configuration, it can achieve a strong balance between the compression efficiency and also the accuracy, model accuracy. So our design places the decompressor between the streaming multiprocessor and L2 cache, and then the compressor is set between the L2 cache and the DRAM bandwidth and the DRAMs. So with this design, so it reduced the total data traffic to the DRAM while delivering a high precision data to the SM for computation. So the decompressor between the L2 cache and L1 cache is decompressing the weights and activation for SIMD compute. So it first fetched the all the metadata, including k-mean pattern, Huffman codebook, and the scale factor, and then perform a parallel Huffman coding, use 64 decoders per 512-bit block. And then the decoded indices are mapped to IP16 value via a shared codebook. And then the outliers will reinserted as needed. So the result is a fully decompressed IP16 tensor, and it's ready for the compute in the streaming multiprocessor. And the compressor is placed between the L2 and the memory. It's used to reduce the KV cache data and also the activation going to memory. So it starts with selecting the k-mean pattern through minimum and maximum compression, and then it runs the parallel Huffman encoding to compress data. And the compressed data are will be packed into the fixed length blocks. And so this process is fully parallel and pipelined to which doesn't introduce much of the latency during the inference. So in the evaluation, so first we compared we compare Ecco with several popular quantization framework like AWQ and Olive, and so we also we evaluate the perplexity on variable llama models and also Mistral model, and almost on all the workload we select here, the Ecco has the best accuracy with during the inference on the compressed model. And then for the inference latency, so we evaluate our implementation on different batch sizes and with different sequence lengths on multiple llama model and also the Mistral model. And then on all this workload, the Ecco is outperform the other popular quantization framework. Yeah, that's the end of my presentation. Any question?